Okay, so we talk about the stability, right? I think using mathematics, but I think it would be helpful if you can see it. If you can see how things move towards their equilibrium point, right, in MATLAB. So I'm going to just show you, I think today and on Thursday, we're going to develop a MATLAB model to show whether the sum of the equilibrium point is an attractor, because they're stable, is the attractor, they attract, so the cancel wins is attractor, is leading to that condition. Okay, and the sum of equilibrium point is not a attractor, we call repeller, is repeller. So it means although they're equilibrium point, but they still don't attract to that point rather than repel away. Okay, so I'm going to show you the MATLAB that we are going to get by the end of Thursday. So let me open the script. I put in the Edge drive, I think. Oh, why there's nothing there? Oh, okay. Okay, so no. So we're gonna generate some kind of script. This is what we're gonna do. Okay, we're gonna run a simulation. So okay, we have this. So we have two equilibrium points. One is represented here. This is x1. This x1 is the density of the healthy cells. X2 is the density of cancer cells. And this is equilibrium point. And this is another equilibrium point. Once we plug into specific values. And we talk about this equilibrium point is stable. Cancel wins is a stable condition. And then the healthy cell wins the remission state is an unstable state. Okay. So we're going to draw some other line. This line just means the cancer cell dx1 0 line. This is dx2 dt9 0 line. So let's pick a few points. Let's pick a few points to see whether they are going to attract to this equilibrium point or whether they're going to attract to the other equilibrium point. We talk about provide little perturbation. So right now, I'm just starting with different initial conditions. Okay, I'm going to make this big. So I'm going to do it here. Why not working? Okay. Okay, I think I clicked twice. So you see attract to the attractor, the stable equilibrium point. So I'm going to start with some other condition. Very close to this healthy cell wins. So it is not attract there. Very close. Is it attracted to this point? It does not. It always attracts to the cancel cell win scenario. Okay. So I'm going to click a few more points. So I also have a point of the cancel cell and the how they change with time. Okay, how they change with time. But I'm not going to show this line here. I'm going to provide a few more points. Okay. Okay, I think it's pretty good. Even you're super close to this remission state, it will still goes back to it still attract to this cancel win scenario because that's a stable equilibrium. Okay, so you can see you always go down. This is unstable equilibrium. Unless you're right at this point, then you're right at this point. Even you're little bit away, provide a little bit of perturbation, and you always start at that point. Okay, so we are going to run this simulation this week, but before we run this simulation, we're gonna look at this, analyze this on the board first. We analyze this on the board. Why the trajectory? Why the trajectory look like this? Why they look like this? Okay, then we can do the math now. Okay. So this sort of indicates the time, this is when you have a this condition. This is after a little bit of time, it goes here, after a little bit of time, it goes here. So how they change with time. This trajectory indicates how they change with time. Eventually, That's it. Okay, so let's look at this. Let's look at this. Let's look at the board. So I'm gonna record the board here so that people. So I'm gonna just stop the sharing for one moment, so I can do the board. So I do want to show the slides I have. So I call this in-class activity. I'm gonna still share the. I don't know why I'm not sharing these slides. I'm still going to share the. Okay, I'm still gonna share this. Okay, so let's do this. We have two tensor growth models. Okay, tensor growth model here. Okay, so the first I'm gonna draw. Let me start with find the lines that represent dx1, 0. Okay, find the lines that represent dx1, 0. So this is also called x long climb. It's called a long climb means that at this line, x1 doesn't change this time. Okay, let's look at dx1 dt equals to 0. dx1 dt dx1 dt equals to, and you see that's r1 x1 1 plus 1 minus, actually 1 minus x1 plus x2 over b minus s x1. Okay, and this equal to 0. This equal to 0, right? This has to equal to 0. I'm gonna just take x1 out. Okay, I'm gonna take x1 out. x1, you can see that I have x1, so this will be r1 1 minus x1 plus x2 over b minus s. Okay, this x1 is already times. Okay, this equal to 0, right? This equal to 0. So this whole thing equal to 0. If this time this equal to 0, so then that means that what can make this to be equal to these are x1 equal to 0 or this equal to 0. So that represents dx1 dt equal to 0. So it's x1 equal to 0 and not and is all, but both of them will make dx1 dt equal to 0, right? And this r1 1 minus x1 plus x2 b minus s equals to 0. So that's very easy. But this will result in, it's very easy to reorganize it with x1 plus x2 equals to, let's reorganize this, equals to b of 1 minus s r1. Okay? So that will make this to be 0. So we have two lines will make dx1 equal to 0. Is this condition or this one, or this condition. Okay, or this condition. Okay, so this is dx1 dt equal to 0. Or what make the other one? dx2 dt equal to 0. That's called x2 long climb. So similarly, I don't have to do it. It's the similar, right? I just replace, I guess, R1 to R2. That will represent this condition, dx2 dt equals to 0. Similarly, okay, this is called X1 non-prime. This two line is called X1 non-prime. Okay, I'm gonna call it X1 non-prime. It's the one here. This is called X1 non-prime. That's whatever you call it. I don't even know what non-prime means, but it's what non-prime. So similarly, what is X2 non-prime? X2 non-prime is what? X2 non-prime. X2 non-prime. X2 non-prime is dx. It's just X2 doesn't change with time. Okay. X2 non-prime is just it is dx2 dt equal to 0. Then we will have either x2 equal to 0 or the same thing like this, but it's just R1 changed to R2, right? Because the equation will be exactly the same. Just R1 becomes R2. Okay. R1. 1 minus S over R2. Okay, so these two conditions, these two are the X, when we represent X2 non-prime. Represent X2 non-prime. Oh, lines like so anyway. These two lines represent the X2 non-prime. So let's draw this. That's why, remember, I draw the two lines. Like, remember just now, I draw the two lines already. What's the two lines? Let me draw the two lines. I'm going to draw it really big. I'll draw it in the X1, X2 plan. Okay, I'm going to draw it in X1, X2 plan. Okay, this is called X1. This is our X2 plan. Okay, X1, X2 plan. So X1 equals 0, which is what? X1 equal to 0 is what? X1 equal to 0 is this line here. Is this line here. Right? It's this line, X1 equal to 0. Oh, what about this line? X1 plus X2 equal to this. Okay. And then this one is the same, is X1 plus X2 equal to this. But which one is bigger, these two values? Which one is bigger? Which one is bigger, this two? This value bigger or this value bigger? Because as R2, the cancel growth rate is faster than the healthy cell growth rate. So if R2 is bigger, then this is smaller. You minus a smaller value, and this is bigger, right? So this actually is bigger. This one is bigger. This one is smaller. This one is a little larger. This one is a little smaller. Just for comparison. Comparisons because R2 cancel grows faster than R2 bigger than R1, resulting this is larger. So this one will be a little smaller. X1 plus X2 equals to something. What does the line look like? What's the slope? What's the slope of this line? If you plot into X1, X2 together against each other, what's the slope? Somebody tell me the slope of this line. X1 plus X2 equals something. What's that? Huh. No, not B. If X plus Y equals to a constant, what's the slope of that line? You plot X against Y. X plus Y equals to 3, say. X plus Y equals to 3. What's the slope of the plot? Okay. 1. -1 is -1. Okay. If you plot X plus Y equal to 3, that will be a line that is 3. Okay, that is sort of intersect with this axis with 3 and intersect with this axis also at 3, which is like -1. Okay, so because these are smaller, so I'm gonna draw it like this. -1. Okay, -1, right? Is a -1. Okay. So what is this value here? What is their What's the value here? What's the value here? What's the value here? And what's the value here? The value for x1. When x2 equal to 0, x1 equal to what? So this, right? So this value here, you can say is b 1 minus s over or 1. That is this value. Okay. That is this value here. Okay. Okay. So same thing. What about this long climb? X2 long climb. X2 equal to 0 is going to be, I'm going to draw a blue line. It's going to be this. Right? It's going to be this, right? That's a blue line. For this one here, x2 equal to 0. What about x1 plus x2 equal to this, which is a larger value? So it's going to be the same slope, but it's larger. So it's going to be larger. So I'm going to draw it like this. Is that right? Okay. So this value here, I'll call this, what is this value here? It's going to be this value here. Okay. So is this value is going to be b of 1 minus s over R2. Okay, is that right? The same thing for this value. So now the blue line and red line, where is their intersects? I think that's our next slide. So where is the intersect of the blue lines and red lines? Where are the intersect? Is this point? Where is the red meet with blue? Here, here, and here, right? Where's the red meet with blue? Is this point here? I'm going to use all the green colors. Is this point here? This is where red meet with blue. And this point here is also red meets blue. Is this red meet with blue? This is not. Is this red meets blue? It's not. Okay, this is also red meets blue. So this is another equilibrium point, but it's trivial. Means there's no healthy cells, there's no cancer cells, nothing will grow out of it, nothing will grow. So there's nothing at all. There's nothing exists. So nothing will grow out of it. So this is sort of trivial equilibrium point is 0, 0. Okay. So that's why there's two equilibrium points here and here. That is meaningful. This is not a meaningful equilibrium point. It's just nothing exists and nothing grows. Okay. But this means what? This means remission state, healthy cell wins. This means the deathly state, the cancer cell wins, right? So it's this and two equilibrium point. So we're going to look at whether the two equilibrium points are stable or not stable. Okay, or not stable. I think I did all this already. So let's not do MATLAB. Let's just do the board first. Then we're going to do MATLAB next time. Okay, so I'm going to move on to the next step. So x1 long climb and x2 long climb. Okay, good. So we have this. So I also call it doesn't matter. Let's just still call x1 and x2. Because I can't do H and C. I can healthy C is cancer. Sometimes people don't like x1, x2, so it's very easy to say. Okay, so let's still use x1, x2. So I wanted to do hand drawing activities. So use arrows to draw the direction in which the density of x1 and x2, you can call H or C. H is healthy, C is cancer cells. Okay, or it is x1, x2. Will move in each region bounded by the long climb. Okay, so there's several regions by this line and this line. What is the direction? Okay, what is the direction? Okay, let's do this. Let's do this. I'm going to erase here. Okay. So we know that this red line indicates what? dx1 dt equals 0. The red line is dx to d. The red line here is d. Is d x1 dt equal to 0. D
dx1 dt equal to 0. Let's see, this is the line for this red line here. For this red line here, I'm going to just for this line here. For this line here is dxt dt. Same thing for this line is dxt dt equal to 0. So above this line is dx1 dt bigger than 0 or smaller than 0? If I say above this line, is bigger than 0 or smaller than 0? Above this line here, above this line, above is everything here, is going to be bigger than 0? Why?
Because you're determining that line is equal to 0 and other.
Okay, so let's look at this. Okay, let's look at this line here. dx dt is equals to x1 or 1 minus x1 plus x2 over b minus s. Okay, that's the line. So that's the line. This is the line. This portion is my line. This portion is my line here, right? This portion is the line here. Or you can say the line is what? The line is also, you can see is x1 to the base, is x1 equal to x2. We just solve it. It's x1 equal to x2 equals to, I think it's b. Is b is also this one, b 1 minus s r1. So on this line, this is satisfied, right? This is satisfied. Let's still look at this one. I think I would look at that one here because this is dx dt. Okay, let's still look at this one here. So on this line, represented by this equation here, is this red line here. If we move up, that means we make x1 a bit bigger, and is this going to negative or positive? So suppose I do have a line here. I have a line here that is satisfied this. Now I'm going to make this x1 to be bigger, or x2. If I make x1 to be bigger, I move to the right. I make from here to here. I make x1 to be bigger. And at this line, at this point, this is satisfied. Now I make this x1 to be bigger, and this becomes more what? Negative or positive? Negative, right? Or the same scenario, if I have this point here, I move x2 up, this is x2. I move x2 up from here to here. So I make x2 to be bigger. This is more what? It becomes negative. With on it, this is precisely 0. But when I move x2 up, or move x1 up, whether x1 up or x2 up, this will, because the negative sign here, so that will become more negative. Okay, x1 is always positive because this is their always on the first quadrant. Okay, so that means if I move above this line, I can see that above the epsilon line, what? That means above the epsilon line, for epsilon line, for this epsilon line, above it, for x1 non-cline, okay, x1 non-cline, okay, then above it, dx1 dt smaller than 0. Can you see that? When it's on it is equal to 0, but once it's above it, you move this up, this will become negative than 0, okay? And then above it, below it, you say below it, dx1 dt bigger than 0. Is that right? So now we know how they move. Whether if they're smaller than 0, means they'll move what? Move right or left. If they're smaller than 0, they're moving with time going on. They're gonna move left. When they're bigger than 0, they're gonna move right. When you provide a little t, they're either increase, x1 is an increase or decrease. Can you see that? Okay, so let's look at x2 long climb. X2 long climb. Let's do x2 long climb. X2 long climb here. Is this the same x2 long climb? Right? I think x2 long climb. The same thing will apply to x2 as well. Okay, so similarly, I just say similarly for x2 long climb, above it, dx2 dt smaller than 0, because x2 will become what? Let me just change this to x2. Just x2. This becomes x2. This becomes x2. Right? That's only thing change. This is x2. This is R1. Just now, this is R1. Okay. Just now, this is R1. Now, this is R2. Oh, I'm going to just change it to red. I forgot subscript here. Just now is 1. Now I change it to 2. Okay. So I change it to 2. Let's change it to 2. Okay. See, I change everything to 2. Okay. So this is 2. This is 2. Okay. This is 2. So the same analysis holds. The same analysis holds. Is that right? Below it, dx2 dt what? Bigger than 0. Is that right? Can you see that? Can you see that? Okay, because when you have a point right on it, when you have a point right on it, this is 0. But once you say, I'm going to move x2 up, means I'm going to make this bigger, then negative then becomes more negative, that because the negative sign. So it's going to be negative. Or you can also move in x1 direction. So that means above it, this becomes negative. Okay, is that clear? Okay, so now let's see. I'm going to erase this. So if I have a point started here, what direction they're going to move? So this is above both, above x1 and above x2. So they're going to take what? This one. Now this point is above both lines, right? It's above both lines. So that means for this point, we have dx1 dt smaller than 0, dx2 dt smaller than 0. Now which direction is going to move? It's going to move to northeast, northwest, southeast, or southwest. So this is east, this is east, this is north. If they're both smaller than 0, if I have a point here, after a little bit of time, where is it going to be? It's going to be this way, this way, this way, or this way. They both, after the post gonna, now, because this point is above both long lines. So I'm going to take this one, I'm going to take this one. So after a little time, if you give a little time, x1 will decrease, x2 also will decrease. So which direction is going to move? Anybody want to tell me? Southwest. Okay. So please, that's right. Let me just write this. This means what? When dx dt smaller than 0, x is this direction. So this means moving west. This means west. This means westbound. Westbound moving. This means what? This means eastbound. This means what? You're moving less than 0. This is x1. This is x1. This bigger, smaller. This means southbound. This means southbound. Is that right? And this means northbound. This is all the 2 to 4 directions. So now I'm going to take this one and this one. So it's southwest. So if you have a point here, it's going to move what? It's going to move southwest. This. Okay. So if I have a point in this one, which one I'm going to take? So they're below both. They're below x1 long climb and x2 long climb. So they're below both. So I'm going to take this one and this one. So that means what? northeast. That means northeast. So this one is northeast. Can you see that? It's northeast. So I'm not even use MATLAB or any programming language. I'm just doing by hand. I'll just analyze all this by hand. How those healthy cells and cancer cells, when they proliferate, they're gonna, because they're competing against each other. It's not like they can both proliferate. It's not like they're both gonna grow because they're competing for the space. So it's not, this means they're both gonna decrease. This means they're both increase. Okay, when the density are too high, for both of them too high, they're gonna decrease because the space is limited. When they're both very low, they're gonna both increase. Okay, what about this region here? If I have something in this point here, okay, so this one, I'm gonna go right here. This is southeast, southwest from southwest. This moves northeast. What about this point here? It's in between. This means it's below this. It's below this one. It's below this one, but above this one. Right? So we take what? Northwest. This one, which is northwest. This is northwest. Can you see that? This is northwest because in between here, this is a below this below. You see, this line here represent. This one here represent dx2 dt equal to 0. So this is what we call x2 long line. This is x1 long line. Okay, this is x1 long line. This is x1 long line. So this line is x2 long line, x1 long line. This one is x2 long line. So now you're in between. It means you're below the x2 long line, but you are above the x1 long line because the x2 long line is higher than x1 long line. So now you go northeast. Okay, can you see that? So we can actually draw this. So let's run a simulation again. Let's run a simulation again to have a better idea. I'm going to close it to see whether they match with our analysis without our analysis using paper and pen. Okay, so if I take a point here, which direction is it going to go? Southwest. Let's see if it's southwest. Oh, why is that working? It is initially go from southwest. It goes southwest. Here it still goes southwest, still goes southwest, still goes southwest, still always goes southwest. Until you cross this line, then you go what? Northwest now. It goes northwest now. Can you see that? No, now my question is, what about when they cross the line? What about when they cross the line? Which direction they go? They go from northwest to south, from southwest to northwest. So when they cross the line, which direction? It has to be west. Okay, when they cross this x2 long line, they only go west. They are not going to go north or south. Why is that? Because this line here represents what? When dx2 dt equals 0, means x2 is not going to change. This is x2. x2 is not going to change. So you have to move left or right, or you have to move east or west. You cannot move north and south, right? So when they cross this blue line here, it has to cross it horizontally, because when they cross it, dx2 dt equal to 0, means x2 does not change. At this moment, it does not change at this moment. Only x1 change. So that means when they cross the line, they go west. And you see that? They have to go west. So this is matched with our analysis here. Okay? So that means I'm going to draw another line here. Means when they cross this line, they go, I'm going to use a different pen. When they cross, I'm going to use this pen. and here. When they cross this line here, they have to go west. I'm going to draw several lines here. They have only go west because on this line, dx2 dt equal to 0 means doesn't change in the y direction, means it only move horizontally. And because dx2 in the because now dx2 dt is smaller than 0, so that means x1 move make it is decreasing, so it's moving west. Okay, great. So I can pick some other point that if I do this point here, it's gonna move what? Northwest. So it's gonna just move northwest. It's just get to the equilibrium point. So I'm gonna pick another point here. So if I pick another point here, it's gonna move what? It's gonna move northeast. Okay, if I pick a point in this region, it's gonna move northeast. I mean, look at it. Okay, so you see it moves northeast, 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 northeast. And then once it crosses this line, it will move what? Becomes northwest. So when they cross this line, which way are they gonna go? It's gonna go up. Because this is gonna go northeast, and this is go northwest, but the the sort of the in between point is when they cross the line, they have to go north. Okay, why they have to go north? Because on this line, dx1 dt equal to 0. This is my x1, so it means x1 doesn't change with time, so it has to move vertically. When they cross this line, it has to move vertically. In this case, because dxt, because x2 is actually, because x2 is what? Is this. dx2 dt is bigger than 0. So it's moving north. When they cross this line, it's moving north. Okay, so that means when they cross this line here, it has moved north. It has to move north. Okay, can you see that? Okay, so now with all this information, without using computer, I'm not going to run the simulation. What does the potential trajectories look like? What does potential trajectories looks like? Okay. What does potential trajectories look like? Okay, and now you can see it here. But even without I showing you this, with all this analysis on their paper and pen, you should know if I give you if I give you a, I'm going to use this side of the board. If I just ask you to draw this, if I want to draw this some kind of representative trajectories with different initial conditions, we have this one here, we have this line here, this line here. Okay, we have this line here. This line here. If I ask you to draw a trajectory, then you have fixed point or equilibrium point. We have equilibrium point here. We have equilibrium point here. Okay, you see, if I started here, it's gonna move what? It's gonna move until it cross the line horizontally, and then northwest, it's gonna go here. Okay, this is sort of like trajectory. You can imagine the trajectory. Oh, sorry. You can imagine the trajectory. It's kind of like that. Okay, once you cross the line, it has to cross. When they cross this line here, it has to cross horizontally. Okay, once they cross this red line, it crosses vertically. It crosses vertically. Okay, it crosses vertically. So if I started here, I go northeast until on this line it becomes vertical, and then go this way. Okay, it's this way. Okay, so you see, one for this line here, if you start here, it goes northeast. When they cross the line, going direct loss has to be processed vertically and then go towards west until it reaches the equilibrium point. So you can start, we can just start with like, for this one, you may not even get a chance to cross. So, right? So, I don't know where. Even when they're very close, you still have the same scenario, same thing. Okay, I think I'm pretty much covered everything. Okay, I pretty much covered all the scenarios. Of course, if you're right here, go directly here. Okay, go directly here. Okay, so that is, I'm gonna just draw a few more lines here. Let me start it here. Oh, it doesn't cross. Let me see here. Oh, it does always cross. Okay, it does always cross. I'm not sure. Okay. Anyway, even you're super close. I'm gonna start with super close to this LC cell remission state. I'm gonna start super close to this point. Are they gonna attract to that point? Let me see. No, let me start it here. Oh, it doesn't attract. So this is called this equilibrium point is a repeller. This is a repeller. This is a repeller equilibrium point. Okay, repeller. This is called attractor. So this is called repeller. Repel, O-R-E-R. O-R? I don't know. Repeller. So this point is an attractor. Attractor equilibrium point. Okay. Attractor means it's stable. It's kind of stable, right? It's stable means you attract everything. It's stable point. Once you reach here, you're not going anywhere. But for the repeller one, once you're there, of course you will stay. But that's as long as you provide a lot of perturbation, you will move away. Okay, there's some other third one for strength. There's some also strength. Equilibrium point means, means like at that point, certain sort of on certain kind of proximity is actually attract, but other proximity is actually repel. So there's other third kind of equilibrium point is either attractor or repeller. Okay, that's sort of strength. Like strength. You have a question?
I think it would be interesting to look at those 2 points at the top very closely, see whether they actually cross or not. You can't really tell.
I could, yeah, I could zoom in later to see whether there's a cross here. Seems to be cross, okay.
Yeah, it kind of looks like it's sort of on the line, but you can't really tell.
Okay, but once you cross, I don't know, once you cross, yeah, anyway. So that is this. So next time we're gonna run the simulation. I think it's a good practice that we don't jump into programming right away, but do everything by hand. So do everything. See, I'm not even solve differential equations. I'm not solving differential equations. I just see how I'm just seeing all this sort of equilibrium, what we call long lines, since don't change with time for one of them. And then I see the direction of this move with regard to time, because when you have a dx dt bigger than 0, smaller than 0, that indicates the direction where it moves. Okay, where it moves. Of course, I can plot this. Let me just show you one more thing. Okay, one more thing. I'm gonna close. I'm gonna show you with the other line here. Okay. Okay, that's still more. Why this one? Okay. So I'm gonna just put this line here. I'm gonna just show you. This is I'm plotting x1 against x2. When I start a point, then they're gonna move with time. They're gonna move with time. Why it's not? Okay, so they're gonna move with time. So this is after a little bit of time. I actually use 4 millimeters. So 4 millimeters. So you can see all of these points are at the same interval. So you can see how things move. Is it faster here or faster here? Which one moves faster? Is it faster here or faster here? Let me just change parameter a little bit. I'm going to change the parameter a little bit. Okay. I'm going to change the parameter a little bit. Okay, I'm going to change my parameter a little bit. I'm not going to make it 0.05. Okay. I'm going to start with here. Okay, now you can see. Is that going to move faster, or is faster here or faster here? When the two are far away from each other, that means they move fast or slow. Because dt is the same. I use the same dt, fixed time interval. Okay, so fixed time interval. When things move fast, they are further apart from each other. When things are closer, they are move slow. Okay, so this you can see. So this, in order to get this, if I solve the differential equation, to get the trajectory, we have to show how fast it moves. Okay, how fast it moves. Okay, I'm going to show you another plot. Oh God. Okay, this plot is what? This plot is healthy cell and cancer cell with regard to time. With regard to time, which one will triumph? Cancer cell will always triumph. Okay, will always triumph because it will always go to this point. Cancer cell will always triumph. I'm going to take a different division condition. You can see how they will change. Okay, so I just put a different point. Now I'm very close to this healthy, this remission state. You see, I'm very close to remission state. You can see, although even originally the healthy cell is much more than cancer cell, but eventually cancer cell always wins because they're so close to this point. There are a lot of healthy cells, but very few cancer cells. But then there's still gonna lose because this is unstable state. They always get to cancer cell win scenario. You see, they're always leading to cancer cell wins, and then all the healthy cell dies out over time. So we're gonna run this and make next time.